K nearest neighbors. The KNN classification is also one of the most often used method for the classification task because it shows it often shows a good classification performance. So this one is one option for classification task. People would like to use this one, but unlike the decision tree and logistic regression, the disadvantage of this method is unlike the decision tree and logistic regression. This one does not provide any interpretation for the classification. So for the classification purpose itself, it's a good option, but uh, if you have to make some interpretation about your classification task, this is not a good option. So please think about it when you choose this method for your classification task. So nearest neighbor classifier, the KNN classifier, requires three things. The first one is a set of stored observations, which means a training set, and it also requires a distance metric, distance measure to compute distance between observations, and the value of k, which is the number of nearest neighbors, should be predefined. So these three things, obviously we should have a training set, and because we have to find the closest nearest neighbor objects, we should be able to compute the distance between observations and the value of k. They are three things that we have to perform the k nearest neighbor classification. Actually, the algorithm itself of the KNN classification is quite simple. Actually, this part is everything about the KNN classification. So to classify unknown record or new objects, what we do is, what this algorithm does is, it first computes the distance to other training observations. So there's a training in the training set there are many observations, and then to classify a new objects, we first compute the distances, and then based on that computed distances, we can identify the k nearest neighbors. So we first, and then we select the k number of data points that are the closest to that new observation, and use class labels of the nearest neighbors to determine the class label of the new data points by majority voting. So for example, in this figure shows the KNN classification where the k is set to 3. So this one is a new observation, new record, and the purpose is to predict the class label of this one. And because we predefined, we set the number of nearest neighbors to 3. What we do is we find the 3 closest objects that are this one, and this one, and all those 3 observations, all those 3 data points have the positive class label, so we predict this new object as a positive class. That's everything. So again, so once a new data point comes in to the training set, what we do is we first compute distance based on the distance matrix of our choice. So we calculate all these distances. Okay, then we have the distances as numbers, and then find the smallest numbers, the closest distances. The first 3 closest observations, we take a look at their class labels, and then by majority voting scheme, we classify this new object. Okay, and that's everything. And the remaining slides explain this in more detail and repeatedly. So this in this slide, the first case is the case of one nearest neighbor. So we just find the only one closest object of this new object. So we in this figure, the purpose is the same. We want to classify this new object marked as cross, marked as X, and the class label of closest the class label of the closest object is negative, so we predict this one as negative. And in the case of two nearest neighbor, we find two nearest neighbors, and because this one has negative class label and this one has positive class label, in this case, because it's the case of tie, what we do is we just randomly assign a class label to this new object. So we can assign either positive or negative by the majority voting scheme. But in the distance weighted majority voting, we naturally actually, because the negative object is closer to this new object, assigning a negative class label might be a better option. So in the case of distance weighted majority voting, I will explain about it later in more detail. Distance weighted majority voting. Okay, and this case is the three nearest neighbor case. So find the three closest data points, and there are two positives and one negative. So we assign positive label to this new object. That's everything. Okay. So this slide shows some mathematical expressions and then describes the algorithm, but the thing is that it's pretty much same as what I just explained. So there are many different distance measures for the continuous variables and distance measures for categorical discrete variables. But in this lecture, we consider the continuous variables only, and we will assume that all those values, the coordinates, are observed in Euclidean space. So to compute the distance between two objects, actually we can employ the Euclidean distance that we know pretty much well. So distance between observation x1 and x2, actually the x1 is a data point on p-dimensional space, and x2 is also the another data points in the same space. So the distance between these two observations is defined by this one, right? This one is the Euclidean distance. So for example, in the case of two-dimensional space, there is a x1 and here's x2. Then what we do is, so this the code x1 code the horizontal coordinates of this data points is x1 1, and what else, the another coordinates is x1 2, and the coordinates of this one is x2 1 and x2 2. Then the distance between these 2 points is computed by x2 2 minus x1 2 square plus x2 1 minus x1 1 square. This is the Euclidean distance, right? So by expanding this concept to p-dimensional space, the Euclidean distance between two objects is defined by this formula. So we just add these squared terms based on the number of dimensions, number of axes. So the algorithm is, let k be, the algorithm is described as below. Let k be the number of nearest neighbors. So we define the number of nearest neighbors by our own choice. So you can use k You can set the k to 2 or 3 or 4 or 5 or even 10. It's just up to you. It's your choice. So this one is the parameter that we have to define, and to make a good choice for this k, in fact, we have to use the uh, validation concept, and we talked about this validation when we were talking about this the decision tree. To determine the size of decision tree, the complexity of the decision tree, what we do is we employ the concept of validation set. So we split the training set into training and validation set, and by observing the accuracy of the validation set, uh, as we goes through the training step, and then we stop the point where the validation error is minimized, right? Do you remember that? So just like that, we have to employ the concept of validation to make a good choice for this k. Anyways, once this k is determined, then we follow this algorithm, and then let D be the set of training examples. So this one is a training set. Then for each test example, for each test data point, Z, which is denoted by X prime, so it is also in the same dimensional space, the same space. Compute the distance between these new objects and other objects in the training set. So here the X is the X coordinates in the training set. Compute the distance between Z and every example X in this training set, and select D sub Z, select a subset from this training set that is consisting of K closest training data points to Z. This is what I explained in the previous slide, right? And then what this line does is, for that subset D sub Z, for the data points, what this summation symbol does is just count the number of examples having the data label, the class label V. So in the two-dimensional case, if V is either positive or negative, in the case of three classes, V can be like A, B, or C. Anyways, so for example, in this binary case, if the class label of ith objects in this DZ is V, then this indicator function returns 1. So this one is an indicator function. This indicator function is nothing but just a function returns 1 if the condition in the parenthesis is satisfied, or return 0 if the condition does not satisfy. Okay, so this function is just count. So for example, in this example, in the case of three nearest neighbor, there are two classes, positive and negative. And in the three nearest neighbor case, positive class is 2 and negative is class 1. Actually, these three data points are the elements in DZ, okay? And then we are taking a look at the Y values of these three data points, and then see if this condition is satisfied. So the case of V is positive. This summation, the output of this summation is 2. When the V is negative, the summation returns 1. And compare these two values, and then we set the predicted label of the new data points using the class label. that is corresponding to the maximum value between these two. So because 2 is greater than 1, we set y prime as plus. Using this example, okay. So it's just the algorithm written in text and mathematical symbol, but the algorithm is pretty much same as what I explained in these two slides. Then distance weighted voting is, instead of just returning just 1 or 0, what we do is we multiply some weight. Okay, so this formula is quite similar with this one, but the difference is that instead of solely using this indicator function, what we do is we multiply a weight w sub I, and that weight is defined by the inverse of the distance between the new objects and ith objects in dz. Okay, and the meaning of this distance weighted voting is training examples that are located far away from the new data points have weaker impact on classification compared to those that are located close to z. So that was explained by this example. So for example, here, actually, if we use the simple majority voting scheme, when v is positive, the summation returns 1. When v is negative, the summation returns 1. So it's a tie. So we randomly assign classification label to these new objects, but let us say that the distance between these two objects is 2, and the distance between these two objects is 4. Okay, then instead of just returning 1, we multiply the weight, which is the inverse of the distance. So in this case, the weight, because the distance between these two objects is 4, the weight is 1 over 4. Because the distance between these two objects is 2, we multiply 1 over 2. So this one becomes 1 over 4, this one becomes 1 over 2, and then we choose a class label corresponding to the maximum value between these two. So we chose the case of the negative class. So we assign negative class to these new objects. Do you understand that? So it means that this object's greater impact to this new object than this one, because this one is closer to this new object. Okay, again, the intuition behind the distance weighted voting majority voting scheme is that the closer objects gives more impact to this to the classification of the new object, and the further object gives weaker impact on the classification of this new object. Okay, that's the intuition behind this distance weighted voting. It's same for the case of k equals to 3, k equals to 4, k equals to 5. We just instead of giving 0 or 1, we give the inverse value of the distance between two objects. Then here's a small example. Here we have a small example consisting of 7 data points, and this is, as you can see from this table, this is a 2-dimensional case. So this part shows the coordinates of the 7 data points, and class labels, 2 class case, class 1 and 2 are there. And then this one is a distance matrix. So to express all possible distances among those the 7 data points, we can make this kind of matrix which is a symmetry matrix. So the distance to the data point itself is 0, so all those diagonal elements are 0, and the distance between 2 and 1 is equal to the distance between 1 and 2. Okay, so this part is the same with this part. And then let us say that we chose k, we chose 3 for k. Okay, then the 3 nearest neighbors of the first object is object 3, 4, 5, because the 3, object 3, object 4, object 5, they have the smallest distance. And then we are taking a look at their class labels. 3 has class 2, 4 has class 2, 5 has class 1. So by majority voting scheme, we predict the first object as class 2. Okay, just like this, we can find the 3 nearest neighbors of each of the data points, and then by taking a look at their class labels, we can make the prediction. Okay, and this one is true class. By using these 2 columns, we can make a confusion matrix. So this one is just this work was done just for training set, but what we really want to do is we want to predict the class of the new data points. And let us say that these 2 data points are new data points, and it's the coordinates of the first new data point is 6 and 7. This one is the transpose. Actually, the convention in mathematical expression, actually we rarely use the column vector. We use I'm sorry, the row vector. So this transpose is just to express that this one is a column vector. Anyways, the x1 axis is 6 and x2 axis is 7, and for the second new object, the x-axis, the coordinate on x1 axis is 4, and the coordinate of the x2 axis is 2. Then please predict the class of x1 and x2. And I'm not going to do this. So please do this by yourself. Do I have to that? So let's go through for just only for this first new object. So what we do is we calculate the distance between this new object and the other object in the training set. So the distance between this one and the first object is, let's square 6 minus 5. Okay, 6 minus 5 square plus 7 minus, what is that? 7 square. That is, what is that? 1. That is the distance between this new object and the first object. Just like this, we compute 7 distances and then find the 3 smallest values, then which means that to find the 3 closest neighbors and then find their class labels, and then by majority voting scheme we can predict the class label of the first new object, and then likewise by following the same way we can predict the class label of this second object. So please do this by yourself, by your hand. And this slide is about the distance weighted voting scheme. So based on the data set given in the previous slide, having just 7 data points, 7 observations, compute the training error rate using distance weighted voting scheme. So training error, yes, it means that based on your choice of k, actually it's almost done. So it means that using these 2 columns, you please construct a confusion matrix and then calculate the training error. That's the first question. I think it can be very easily done. And oh no, not that. Sorry about that, because we have to use the distance weighted voting scheme. So not not by just counting the class labels. Instead of counting the class labels of the each class, you have to compute the, you have to multiply the inverse of the distance to each of the to each of the result of this indicator function. So please uh, yes, please do this yourself. Do this by yourself. Okay, by this distance weight, I'm pretty sure that you know what this distance weighted voting scheme. So using this one, using the distance weighted voting scheme, please find the training error, which means that you have to make the predicted class column and then make the computation matrix and then compute the training error. And then predicted classes of the x1 and x2. Here the x1 and x2 are the new data points shown here. So predict the classes of x1 and x2 using the distance weighted voting scheme as well. Okay, so please do this by yourself. Yes, because it's pretty easy, so I really don't have to show that. Okay, then actually here is the issue that we have to choose the value of k, the number of nearest neighbors. If k is too small, then it is the classification is very sensitive to noise points. And if k is too large, neighborhood may include points from other classes. Actually, this one is shown in this from this example. So let us say that we want to predict the class label of these new objects located at the center of this figure. Then which class label should be assigned to these new data points? What do you think? Positive or negative? I think the positive, because all around these new data points, all of these data points have the positive sign only. So I think it should be predicted as positive. So if we specify k, if we set the k to 3, 1, 2, 3, 4, 5, then 5, 6, 7, even until 8, 9, it this one is going to be classified as a positive. But if we set the k uh, to the value which is greater than 10 or 11, 12, then because there are more negative classes around this place, so it's going to be predicted as negative. So if k is too large, then we may get some, incorrect result. But if we choose very small value for this k, then the classification becomes very sensitive to noise points. It means that actually this issue is corresponding to the overfitting problem. We have talked about this overfitting problem in the decision tree class, right? So if we make the tree too complex, which means that there are so many leaf nodes, then it works very well only for the training set, but sometimes it doesn't work well for the test set. So if we specify k to very small value, then it works very well for the training set only, but it's highly possible that it does not work well for the test set. So this one is corresponding to the overfitting problem. And let's take a look at these two figures. And in this example, there are three classes: green class, yellow class, and blue class. And if we set the k to 15, actually these these solid lines is the decision boundary based on 15. So for example, and then this area, the green colored area is the area for the green class, and then here blue colored area is the area of the green class, and then yellow class, this area is seems here. Okay, so here this green class of object, green class object, green class object, green class object, they will be misclassified. These are misclassified. These blue points, they are misclassified. But this one is better, I guess. If we set the k to 1, which is very small value, actually the decision boundary becomes very, very complex. So even though it works very well for this training set, the future prediction of the future classification may not that good, maybe not that good. Okay, absolutely, it's highly possible that we're gonna get a high test error, high test error. Okay, so it seems that yes, it seems that the decision boundaries, the solid lines, it seems very complex. So this is not a good case, and this one is a better case than this one. So we have to choose a proper value of k in k nearest neighbor classification. So what we usually do is, just like the decision tree, once we have a data set, we split the data set into two parts, training and test. And we split this part again as training and validation. And then use this part only for training. Actually, this algorithm doesn't train anything, but based on your choice of k, so set the k to 1, or set the k to the choice of your the value of your choice, for example 3, and then predict the class of the data points in the validation set based on this training set and based on the choice of k, and then predict the class label for the validation set and see the validation error or validation accuracy, and observe that validation accuracy by varying the value of k. Okay, so you can, I think you can construct this kind of two-dimensional graph where the x-axis is k, so change from 1, 2, 3, 4, something like this, and so on, until some enough large number of k, for example 20. So you can test to the number that you want to test, and then the y-axis is the validation error. And then by changing the value of k, you can observe the validation error, and then, for example, the graph looks like this, then you choose the value of k at the minimum validation error. Okay, that's the way of choosing this model parameter in k nearest neighbor classification. Okay, everything is clear? Okay, there's nothing difficult in the k nearest neighbor classification. It's very simple. Algorithm is very simple, and what you really take care of is the value of k. So this is the last slide in k nearest neighbor classification. So there are some issues. The scaling issue. The attributes may have to be scaled to prevent distance measures from being dominated by one of the attributes. Here is an example. So let us say that in our training set, there are three x values. X1 is height, X2 is weight, X3 is income. And height varies in this range because the scale is meter, is 1.5 and 1.8, or 1.7, even 2.0. The value of height varies around this range, but if the scale of weight in our training set is the pound, then it varies this range, right? So the variance becomes bigger. The variance of this attribute is bigger than this one. So if we employ the Euclidean distance and even bigger for this income, it is 10,000 because income is the unit is US dollars, so $10,000 and $100,000, $1 million. It varies a lot. So if we employ the Euclidean distance, the distance value itself is totally dominated by income because its scale is the largest. Okay, so for example, there are two people. The person A, his his height is 1.6 and okay 1.8, which is what I hope. I'm sorry. Okay, and the weight is, instead of a pound, let us use the kilogram. The weight is this guy is 72, and the income is how to say 3,000, 4,000, 50,000, 50,000 US dollars, which means that which corresponds to about 5천만 원 in Korean won. And person B, this guy is, the height is 1.7, weight is 65. This guy seems pretty much myself. And the income is hopefully okay 200K. Okay, then if we employ, although no, this is not my annual salary, so please do not misunderstand. Okay, and but this one is pretty much myself. And okay, so if we employ, it's quite funny that actually in front of me there's no one. But okay, so if we employ the Euclidean distance, then using this low data set, then the distance between these two guys becomes 1.8 minus 1.7 square plus 72 minus 65 square plus 50K minus 200K square. So the distance is totally dominated by this value because it has a greater unit. Okay, so because of that, actually it is more often recommended that we have to scale out these so that these three the attributes contribute equally to the distance. So attributes may have to be, actually sometimes must should be scaled to prevent distance measures from being dominated by few of the attributes having the larger scales. Okay, that there is an issue, scaling issue. So you can either standardize the data set, which means that we can subtract each of the columns from the mean and divide by the standard deviation. You can either standardize stand standardize or normalize. Normalize means that, for example, 0 1 0 1 normalize means that you can divide the data, you can divide a column by its maximum value, then the range of that column becomes 0 to 1. Okay, do I have to show that? Okay, because we have a little time. Let me show that. So for example, the music data set. Okay, yes, this one has quite big variance, which means that this one has quite big scale, and this one has a little smaller scale. So what we can do is, let me just copy those x variables to another worksheet. Actually, you can do this using R software. And then the normalization is this one. Let me first figure out the maximum value of the first column. Is this one, and I'm gonna normalize the first column by dividing this value by the largest value. Oops, I'm sorry. Over this value. And then I have to fix this maximum value. Then this one is a normalized column of the first column. We can do that in the same way for the remaining columns for the 0, 1 normalization. Okay, then the values ranges from 0 to 1. That's the way of normalization. And standardization is we first figure out the average of these values, and then is that SD, standard deviation? Okay, standard deviation of the sample of those numbers, 54 numbers. Then this one is average, this one is a standard deviation. That what I'm gonna do is I subtract the mean value, and then divide that value by the standard deviation. Then this one is the standardized value of this one. So because I have to fix this cell and this cell and apply for the remaining rows, and then this one is the standardized value. Okay, to make the mean 0 and to make the variance 1. And you can make this kind of transformation using the R programming in easier way. So there is a scaling issue, and KNN classifiers are lazy learners. This one is a lazy learner. Why? Because it does not build models explicitly. Actually, even though we have a training set, it does nothing. It does nothing until when a new data point comes into the training set. As soon as a new data point comes into the training set, this algorithm begins to compute the distance between this new object with other objects in the training set. So it does nothing. So that's why we use this lazy term here. So unlike eager learners such as decision tree or logistical regression, this does nothing, and classifying unknown records are so relatively expensive, computationally expensive. So if imagine the situation where we have a training set consisting of 100,000 data points, then even for a classification over just a single new data points, we have to compute 100,000 distances, right? So if the size of training set is large, then KNN, k-nearest neighbor, may not be a good option. It's not a good option. because it takes long time to compute the distances between the new data points and the other data points in the training set. Okay, that is the disadvantage of the k-nearest neighbor. And yes, it is shown here. As I just explained, finding nearest neighbors is computationally expensive. It requires lots of computation. So we sometimes need to employ some sophisticated method such as KD tree. Actually, this KD tree, I think people in computer science department, they learn this structure in I think the data structure class. And I remember that when I was a undergraduate student, I took this data structure class from the computer science and engineering department, and then it was quite useful. And they teach about queue stack and trees and their structure to efficiently retrieve the information, data from the database. So uh, this class is recommended to take. Okay, if you uh, if you want to take this class, then I recommend that. So I'm just giving you the name of tree. KD tree is to find is quite specialized to find the nearest neighbor points, k nearest neighbor points. So I'm just giving you the name of the data structure for finding nearest neighbors. And almost all commercial softwares and even the R software, almost all softwares, the finding nearest neighbor is based on this KD tree, implementation of the KD tree. Okay, so that's everything about this slide. And even though there's not our example in this slide, because we have little time, let's do our practice using what I'm thinking is using that music data set used in decision tree algorithm. So still I have the data set in my folder, this one, music data set. So read that data set into my R session d.music using read.csv. Sorry, read.csv. File name is music.csv. And there is a column name, header is true, and separation symbol is comma, and bring into my R session, and data music looks like this one. I'm not going to use the first two columns, so d.music is I'm gonna take the remaining 1, 2, 3, 4, 5, 6 columns. I'm gonna exclude all rows and exclude first two columns. Then okay, only the class columns and the other columns. So to use the k nearest neighbors, wow, I have to standardize or normalize this data set. I'm gonna skip that step, but you can use, just for information, you can use the scale function. Do I have to show that? The scale function. This function can do both standardize and normalize, okay? I'm gonna skip that. Anyways, the k-nearest neighbor classification can be done by using knn function in class library. So you have to attach class library in your R session using library function. Actually, this package is a default package. If you install R software, then this package is already installed in your R session. Class, where is class? There must be a class. Yes, here's a class library. Once you attach this class library into your R session, then you can use this KNN function, K nearest neighbor classification, and to predict the class labels, I have to split the dataset into two parts, training and test set. Let me do that. D dot train. D dot rock is D dot music follows D dot music type equals to block. No, I have to select rows which y values are rock, so I have to specify here. Okay, so there are 30 rock musics, and then I'm gonna make the classic, the label classical, the value is classical. Okay, there are 24 observations having the classical value on y class label. Because it takes long, I'm gonna pause at this moment and then we'll be back after typing the necessary comments. So what this line does, we just extracted the rows having rock values on the class column, and this one is just to extract the classical musics by checking these conditions, and this one is, so it was stored in the d.log and d.classic, and d.log is divided into two parts, training and test. So I just select the first 21 observations for the training set, and the other remaining how many observations are there? The test is the rock test. 9, the remaining 9 objects for the test set, and the first 15 objects is selected for train from the d.classic dataset, and then the remaining d.classic test. Remaining 9 objects is selected for, they are selected for the test set. So by using this rbind function, I use the training set and test set so that each of the set consists of both classes. Okay. So by running these whole lines, I prepared the d.train consisting of both rock class and classical class and a test set. Okay. Then what I'm gonna do is we will predict the class labels of this test set. Okay, using this KNN function. And first input argument is the training set, matrix or data frame of the training set cases. And then the second input argument is the test set, matrix or data frame of the test set cases. A vector will be interpreted as a row vector for a single case. And CL here is the vector of the two classifications of the training set. Okay, so we can use KNN function. First input argument is a training set, but should exclude d.train should exclude the training column, the class column. Okay, and we want to predict the classes of test set, so we have to exclude the class label, and the true class label of this training set is this one, type, and the fourth input argument is the number of k. So let us just simply choose k, choose 3 for k, 3 nearest neighbor classification, and then L is minimum both for definite decision. Well, I think that's enough. So by learning this can and command, you can make the prediction, as you can see from here. Okay, so you can change the number of nearest neighbors here 5, then you're gonna get another prediction. So let us say that this one is the predicted class of the test set, pred.test. In the case of 5 nearest neighbors, and then make the confusion matrix using table function. The true class is the dot test of the type column of the data test, and then the predicted class is pred.test. Okay. Then there are 13 observations correctly classified and 5 classical observations that are misclassified. Okay. Then how about by changing this one to 3? Same performance, and then choose 1. It's worse prediction, right? By specifying the small number of k. Then how about 10? Same performance. Anyways, just like this, by taking a look at, so let us, you can consider this d.test as a validation set, and then by learning several times, by trying this knn function, k-nearest neighbor classification, with the change of this number of the nearest neighbors, which is k, you can observe the performance, and then you can even calculate the error rate based on your choice of k, and then choose the best k, which is corresponding to the minimum, the prediction error. Okay, that's the way of choosing the best value of k based on your application, based on the data set. In this case, the music classification. Okay, so that's everything about the k nearest neighbor classification. So please again, in this example, I guess which column, this column, the LVR column, almost dominates the distance measure. So before doing this, please standardize or normalize the x data, x part, the x variables. So that's everything about the k-nearest neighbor classification. Thank you for your attention. Next time we will learn about another classification technique. Thank you for your attention.